Introducing the new adhesion analysis method for advance, which can be used to quickly and easily calculate scientific parameters for the interfacial contact between solids and liquids. This method will help you to optimize processes such as adhesion, coating, or printing. Adhesion analysis is available for Kruss force tensiometer and drop shape products. To start an adhesion analysis, open a new measurement workspace. In the Data tile, prepare the measurement data which is to be investigated. The data can be taken from existing measurements or input manually. Here, we are using data from two solids, polymer 1 and polymer 2, which are taken from our own measurements. The values of the liquid samples, in this case 2 adhesives, are entered manually. To do this, click on the Add Substance button. Then enter the values for the surface tension and the dispersed part of the substances. The polar part and polarity are automatically calculated from the entered data. In the Results tile, a clearly organized table displays the values calculated from the adhesion analysis, which result from the combinations of the specified substances. The following values are calculated: work of adhesion, interfacial tension, spreading coefficient, and contact angle. For a more detailed evaluation of specific data, the values can be shown or hidden in the Results tile. In the following example, we use the existing combinations to determine the best possible adhesion between a solid and a liquid, and then optimize it according to our requirement profile. A high work of adhesion means a high adhesive force. The table clearly shows that the combination adhesive 2 and polymer 1 has the highest work of adhesion. For our example, we will examine this combination in more detail. The Chart tile displays the results in the form of contour lines, also known as ISO lines. The lines refer to the selected sample. Each contour line in the chart has a fixed value for one of the 4 selectable parameters: work of adhesion, interfacial tension, spreading coefficient, and contact angle. The lines show which combinations of polar and dispersed parts of theoretical substances would result in the corresponding calculated value. On the x-axis, the polar part is shown. On the y-axis, either the total surface tension or its dispersed part can be selected. In our example, we assume that the adhesion is to be optimized by surface modification of the solid, while the values of the adhesive are based on the fixed properties of the supplied products. For our polymer optimization example, we select work of adhesion as the property and the non-variable liquid adhesive 2 as the sample. Looking at the chart, it is immediately clear in which value range polymer 1 and polymer 2 are located. Through zooming in by using the mouse wheel or the slide bars on the sides of the chart, a more detailed view can be obtained. According to the chart, polymer 1, with a dispersed part of 29.9 and a polar part of approximately 7 millinewtons per meter, in combination with the adhesive 2, produces a work of adhesion of approximately 61 millinewtons per meter. In our example, we assume that a work of adhesion of approximately 67 millinewtons per meter is required for an optimal adhesion process. The chart clearly shows that we need to increase the polar part of our solid, for example through plasma activation, to approximately 16 millinewtons per meter in order to achieve the required adhesive strength with our chosen adhesive. Similarly, by changing the polar part of the solid, you can view the effect on other properties, for example, the interfacial tension. The highly structured and innovative adhesion analysis method for Advance provides you with the ultimate tool for the precise analysis and optimization of your interfacial process.